Assalamualaikum warahmatullahi wabarakatuh. See you again. Today, 16 January 2021. I am Nanang Dwi Suprapto. I would like to share with you about industrial instrumentation and process control basic knowledge. About process control. In almost all industrial process application, control of process variable is very critical to the safe and efficient operation of the process. The most common variable control are pressure, flow, level, and temperature. Self-regulating process. Self-regulating processes are processes that are inherently self-regulating. Self-regulated processes have built-in feedback characteristics that cause the process to tend toward self-regulation. Just an example of a self-regulating process is a tank of water with an input of water entering the tank and an output of water leaving the tank. Let's say the water level in tank is constant at 10 inches. Water enters the tank at the rate of 20 gallons per minute and leaves the tank at the rate of 20 gallons per minute. As long as this balance is maintained, water level in the tank will remain constant at 10 inches. What happens if the outlet valve is open and 1/8 of a turn and water leaving the tank change to a rate of 25 gallons per minute? Since this is a self-regulating process, the level will actually stabilize at a new position and maintain that position. Flow out of the tank is proportionally to the square root of the differential pressure across the output valve. As the level decreases, the differential pressure will also decrease, causing the rate of drainage to decrease. At some point, the drainage rate will once again equal to fill rate, and the tank will reach a new equilibrium point. Time constant. Every self-regulated process has a time constant associated with it. The time constant is the amount of time it takes the process to change 63.2% of the final value of the process. In this example, the process changed by 10%. The time it takes to change 6.32 inches, which is actually 63.2% of 10 inches, is the time constant. It takes 5 time constant in order for the process to complete the total change. Process gain. The time constant is affected by the capacity of the process and the process resistance to change. The larger the process capacity, the longer the time constant, and the more a resistive element in the process, such as small pipes, penetrations, valve, etc., the longer the time constant. Dead time. Dead time, by definition, is the time difference between when a change occurs in a process and when the change is detected. Dead time exists in all processes and is a factor in the control loop control, which must be addressed when turning the loop. Non-self-regulating process. A non-self-regulating process is one where the process does not tend towards self-regulation. These processes have no self-regulating feedback characteristics and will tend toward being unstable if not controlled externally. Just for example, the water level in tank is constant at 10 inches. Water enters and leaves the tank at the rate of 20 gallons per minute. In this process, instead of having discharge valve on the tank, a positive displacement pump is used to drain the water. As long as the balance is maintained, water level in tank will remain constant at 10 inches. If we decrease, if we increase the discharge rate of the positive displacement pump to 25 gallons per minute, what will happen? Initially, as with the self-regulating process shown before, we are removing 5 more gallons per minute from the tank than we are putting in the tank. This causes the level to drop. However, unlike the self-regulated process, this drop in level does not affect the flow out of the tank. A positive displacement pump will discharge a set flow rate regardless of head pressure. The pump will continue to discharge at the rate of 25 gallons per minute until the tank is completely empty. Process control terminology. Control variable, measured variable, set point, error signal, controller output, manipulated variable. Process control terminology. The various components that make up a control system are seen in the diagram here. Each of these components has its own characteristic, and changing any single component will change the overall response of the control loop. A simple control loop shown above is comprised of 6 major parts. Control variable. Control variable. The control variable is process parameter being controlled. In the example here, water level in the tank is the control variable, but it can be any process you wish to control. Controlling this variable is primary function of process control. Control variable is indicated with the letter C. Measured variable. Measured variable The measured variable is the electronic or numeric representation of the value of the control variable. The measured variable typically comes from a transmitter, which measures the control variable and procedure an output representative of it. In the example here, the level transmitter is measuring level in the tank, the control variable, and converting that level to 420 milliamp signal. Measured variable is indicated with the letter P. Set point. Set point, the measured variable is sent to the controller in the loop, where it is compared to, to a desired value called the set point. The set point and the measured variable are compared in order to produce an error signal. The set point is often manually entered by operator, but it can also be automatically obtained from other systems. Set point is indicated with the letter R. Error signal. Error signal basically is measured variable minus set point. The error signal is the difference between the measured level and the set point. It can be either a negative or positive value. The error signal is then added the base signal level of the controller to create the controller output. For example, the base or initial output value of the controller may be 50% with a zero error signal. Any error signal developed by the controller is then added or subtracted to this 50% base level. Error signal is indicated with the letter E. Controller output. Controller output is simply the total output of the controller. With the controller in automatic, the output is calculated by the controller itself. If the controller is placed in manual, the output can be manually adjusted to any desired position. Controller output is indicated with the letter P. Manipulated variable. Manipulated variable is the parameter that is adjusted to bring the process back to the desired set point. The manipulated variable in this case is the water entering the tank. The water flow is manipulated in order to keep the level constant as the output demand changes. Manipulated variable is indicated with the letter M. Three types of control loops. A. Open loop. B. Feed-forward control loop. C. Feedback or closed loop control loop. Understanding a process control loop. You can see here this is the process. This is the final control element, which is control valve. This is controller. This is measurement, which is can be sensors and transmitter. The major component, a traditionally control loop, has three components. First, the controller itself. Second, a sensor or transmitter and transmitter. Number three is final control element, which is control valve. You can see the animation here. Set point here called SP. Set point actually in this animation say that set point to the controller, which is set. Here is actually a error. Error, the difference between set point and PV, measured process variable signal, or PV. Yeah. Controller here, output of the controller called controller output signal, or CO. And then valve, final control element, the output called manipulated variable. And then this is process. Output of the process is process variable. And then feedback detected by sensors, and then signal and transmit, and then check how is the difference with this set point. And then disturbance here. So this is actually general control block diagram. Please see carefully of the flow. This is mathematic form of the controller. PID. P is proportional, I integral, D is derivative. Set point in this display, you can see set point, which is R, error is E, proportional, which is Kp and E times by E, integral Ke integral Et, derivative Kd, and differential E. The output of the controller, here control variable called UT. The process variable output from the process of the plant is YT. The mathematical form UT equal with multivariable, which actually equal with proportional gain times by error plus integral gain which is Ki integral 80 plus derivative gain, differential E. So PT is proportional gain, PI integral gain, CD derivative gain. Error ET equal with set point minus process variable. I would like to simplify on the diagram. SV set point, PV process variable, E error, which is SV minus PV, T proportional, I integral, D derivative, output of the controller called CV control variable, and output from the valve actually manipulated variable. In this case, CV equal with MV. Output from the process is process variable or PV. Proportional gain P. You can see here the diagram, which is I and T, integral and derivative, we assume 0. So that CV, control variable proportional, equal with multivariable, equal with TP times by error. Proportional gain, P, it's called proportional band or PP. Percentage proportional band equal with 100 divided by P. Percentage PB called KP, constanta P, which is equal with 100 divided by P, or we call gain. This parameter to determine how fast the system responds. You can see here how the performance of proportional. Now, we're trying to increase P by 18 by 8 and P just setting by 1. How's the response? How about if P equal with 8? How about if P equal with 1? So basically, proportional band is equal 100 divided by 18, which is by P, equal with 5.5. Proportional band, so the P8 is basically 100 divided by 8, which is equal with 12.5. If P equal with 1, so the proportional band equal with 100. How about if we decreasing proportional band and increasing gain or P? With the example, PB 118, PB 1 per 8, PB equal with 1. What is the response? Like this. How about this PB 1 divided by 8? How about this PB equal with 1? Alright, next. Integral. Integral equal with reset. I think you still remember the mathematical here. Ti equal with 1 divided by time. Ti, integral time. So that this is actually talking about the frequency. This parameter to determine how fast the steady state error to be removed. Ti and Ti here is basically time in second, yeah, or time in minutes. Talking about the repeat in second, repeat and second per repeat, or repeat per minute, or minute per repeat. Next, Ti equal with 1 per time integral. This one basically is total from this. How is the performance for the integral like this? This parameter is to define how fast the state error is removed. Okay. Example, increasing Ki, constant integral, or reducing time integral. Example, Ki equal with 1. Ki equal with 1 per 5. Ki equal 1 per 10. How's the response? This is Ki equal with 1. This is the performance response. Ki equal with 1 per 5. This is response. Ki equal with 1 per 10. Derivative. The formula, we are believing that you still remember the mathematical model. This is the mathematical model. Derivative in second or minute. This mathematical model. So basically like this. The derivative is the delta between process variable on the T2 minus process variable at T1 divided by delta of time between T2 and T1. Common use in control is proportional, and integral. This is quite common use in the control system in industry. The other one, common use in control is PID, which is proportional, integral, and derivative. Very rare use in control is proportional and derivative. This is the difference between proportional versus proportional integrative, integral versus proportional, integral, and derivative. The response like this. Example PID controller in temperature control. You can see here PID controller here actually to control the temperature in the furnace, and then output going to the control valve, yeah, so that you can adjust how much the P proportional, then integral Pi and time derivative. So you can see how the response of the controller. The other example, the ID control in flow control. This flow, flow meters, this control valve, and this is PLC as represent of the controller. You can see here PID controller, then you can set how much the key P, Constanza proportion, time integral, and time derivative. So you can enter on the maximum value, and you can see how much the SV set point and how the response is TP. Another example, which is PID controller in speed control motor, which is in this application, PID control is to control speed of the motor. Speed of the motor. Another example is PID control in the steam drum water level control in boiler. Steam drum level control in boiler. So here is a controller, level indicator controller. This is valve, and this is actually the level transmitter. Okay, this is a typical response for the PID controller. You can see here FKP, PI, PD. All right. Okay, this is the, you can see here how is the performance. If proportion at KP increasing, if PI integral increasing, and how about if PD increasing? How is combination? This is actually the optimum. I repeat again, if you like to adjust to set how much the KP, PI, and KD, and this is the optimum number. I repeat again, okay. All right. Example feedback control. This is talking about home heating control loop block diagram. Please see carefully here. It is a room heating process actually to be controlled, yeah, about the temperature. This is a room heating process, hot water control valve, thermostat, controller. This is the brain, this is the control itself. And then disturbers. This is sensor and transmitter. Yeah, start with that home heating system. A home heating system can be a simple on-off control or proportional control by adjusting the amount of hot fluid by throttling a control valve. Nevertheless, we introduce the idea of control loop diagrams by presenting a home heating system in the same way we would a more sophisticated commercial control application. Starting from the far right in the diagram above, our process variable of interest is the house temperature. A temperature sensor, such as a thermistor in a modern digital thermostat, measures temperature and transmits a signal to a controller. The measured temperature's PV signal is subtracted from a set point to compute controller error, which is E equal with SP set point minus process variable. The action of the controller is based on this error. In this example, home heating system, the control output feeds a varying or proportional milliamp signal to a variable operating solenoid or servo valve, our final control element that controls the flow of hot water. As the energy output of the furnace rises or falls, the temperature of our house increases or decreases, and a feedback loop is complete. The important element of a home heating control system can be organized like any commercial application. Control objective: maintain room temperature at set point in spite of disturbance. Process variable is actually room temperature. Measurement sensor is temperature sensor, which is detected by thermistor. Measured process variable PV signal is signal transmitted from the thermistor. Set point, desired room temperature. Controller output CO or manipulated variable MV is actually signal to the variable operating solenoid valve. Final control element is variable operating solid valve to control hot water flow. Manipulated variable is hot water flow rate to the chamber. Disturbance in this case is heat loss from the door, walls, and windows. Changing outdoor temperature, sunrise and sunset, and rain. This is considered disturbance. With the loop closed as shown in the diagrams, we set to be in automatic mode and the controller is making all adjustments to the final control element. If we were to open the loop and switch to manual mode, then we would be able to issue controller output command through buttons or a keyboard directly to the final control element. Therefore, open loop is actually same with manual mode. Closed loop is actually same with automatic mode. Reference. This presentation we get from some information coming from instrumentationtools.com, Wikipedia about PID controller, Araki PID controller, Richard E. Bellman, and so on. Please subscribe, like, and share if you think this video gives you benefit. Thank you for watching.